We are OYU, All Your Universe, for cross design system thinking, instructed by Professor Chu Jung-ki. We're glad you are here. In this video, we'll take you on a journey through the creation of OYU Monorail Telescope, a truly amazing device. This semester has provided us with numerous opportunities to push our limits and try new things that we have never done. We are grateful to the entire team for helping us to finish this telescope, especially Long, who had helped the most due to our different schedules to finish our products and come up with new ideas that help us to see what they would look like. Therefore, his voice will not be in this clip since he deserves a day off. Furthermore, we can use such machines with the help of our instructors, Vicky, Jufu, Jutai, also Taiwan and Taiyu, and TAs who also spend time guiding us.
Let's go back to the beginning when we first met each other and always confused by such proposed ideas for this final project. Each person had each expectation and dream as well. Even most of us know nothing about astronomy. But why we choose to do this? Let's see.
The first period was brainstorming. We started with team expectation sharing. Depend on design system thinking method, we know our teammate boundary, their strength, and their weakness, so we can support each other. Working style were really important lessons to learn to respect individual working style. Instead of looking the different time working, we focus on what we have done after a week, and we unify how we communicate to teammates effectively. Choosing ideas were the period that we learned to answer the big questions. How did we choose the topic that was workable and visible? Because we don't have a gap knowledge about engineering, so we learn to build foundation by researching, discussion, and consulting. Therefore, we can vote suitable ideas for us. The last way was consulting with Thầy. This led us to understand which ideas create feasible products. Three key filters we always remember is money, the time limitation, and the reference.
So, let's go back to the beginning when we came up with this idea. Why telescope? Why the subject that even our team members aren't into it?
In the session, in the understanding and observer part, we try to find the answer to the question, how did we gain the picture? So we use different methods such as survey, interview, or 5-minute questions. So we learned that the product must meet the actual needs of people, and there is nothing better than listening to them. From there, we confirm who the stakeholder we want to target, and we clearly define the project's problem statement.
For more insights, we create surveys and mini interviews using an empathy map to reflect on students' STEM and physics learning. From that, knowing the lack of practical parts and motivation in learning, those led us to dive deep into engaging student careers to learn. So the problem statement is stated that how might we encourage STEM interest from high school students around Vietnam to satisfy excitement and practicability considering the limited budget and guidance. The goal is to engage as many students as possible for both no background or guidance provided students with students in STEM clubs who we assume that it can have some basic backgrounds and have the ability to pursue and develop new features and functions in upcoming products. Students must work and learn the same themes. This demonstrates the need for the products to be based on high school level knowledge. STEM and coding are also needed as well. That's the reason why we decided to build straightforward automatic telescope mount with a telescope that can be made cheaply and easily from resource available in grade 11. There are more steps to process. Now let's talk about ideation.
The main goal of ideation stage is to use creativity and innovation to develop the solutions. Therefore, bringing ideas into the real practice is quite different and difficult. That requires all of my team members to be flexibly adapt. At the beginning of the version 001, once we have decided the idea and gone through the first sketch, Fusion draft, we have joined hands directly to execute the product step by step. Although the size of the drawing of this telescope in Fusion looks quite normal, in the real world, the size of the product is actually too large for our motor to work, to move. However, we have enough time to switch to another approach, tightening the telescope to be feasible. Because during our team meeting, we also acknowledge such an important role of ideation stage. We have sped up drafting Fusion sketch and spend most time testing, working on some parts of the product for experiments. But as you can see here, we have made the telescope version 002 so small that we cannot even see the sky. During the process, we still stick to the main purpose of the product to be rotatable. However, we are not satisfied with such kinds of inconvenience. So we have come up with the final version, telescope version 003, with a medium size, which can fit both of our motor weight and our functionality expectations. You can see here. But we do have a limitations that our motor cannot rotate more than 180% degree. So that means if you stay in the north, you cannot rotate until the south. So that's kind of problem. So during the process, we have learned that we always need to prepare time for testing and practicing doing products as soon as possible. Moreover, we should also break down the steps with specific goals. For example, initial stage to focus on the functionality for the motor to work. Next, we can focus on user experience and operator's preference, right? This clear outline can help us speed up the progress. Finally, it is important to learn from failure. This is really important. Whether the telescope is too large, too small, after each time we learn the lesson to give out the most accurate measurements for our product.
Yay! The first part was done. Now is the time to make it real, our prototype.
In the prototype part, Fusion Sketch, we have learned that Fusion Sketch and real product can be closely connected. Sometimes we need to use the measurement of real products to apply for Fusion and vice versa. Fusion requires a careful calculation to fit well with the real products. However, with Fusion Sketch, working on a product can be operated really easily. So you can see here we have really carefully prepared with our sketch here. To come up with this final version, we have moderated it quite many times.
Our team has been through 2 prototypes. The first is a simple cardboard prototype. This prototype is a landmark in our process, as it helped us realize that the final product needs to be scaled down to 50% in size. This prototype took us a few hours to build, and the result was satisfying. The second prototype is also our final product. For this prototype, we've been through 5 stages to build it: laser cutting, assembling the mica parts, CNC cutting, gluing the wooden stand, and putting everything together. The first step is laser cutting some mica parts. We used the 5mm and 3mm mica primarily. Yu Feng helped us repair the mica plates to fit in the laser cutting machine, and Yu Tai instructed our team on how to use the device. We made the telescope bearing, rocker boxes, and a 200mm diameter plate out of mica. Thanks to Lum's Fusion 360 file, we had all designs fully repaired. However, the difficulty was that not every team member was familiar with this machine. I needed to instruct some of them, and they soon mastered it. In the clip is V cutting the telescope bearing. Our stuff is done, and box seal now. You know, the feeling is very satisfying.
Nice.
The next step is assembling the mica and mechanical parts. Firstly, we worked with the PVC pipe representing a real telescope. We measured at which point we should put the PVC pipe to the telescope bearing so that the servo motor lost the least weight. Usually, the center is the perfect point, and our case is not different. Then, I need to cut PVC pipe to shorten it. The blue mark indicates where the cut should be. Thanks to taking instruction, I could cut the pipe quickly. The machine was really deafening and scary, by the way. Then the pipe was ground. The next step to be taken is to glue the 200mm diameter crown box to the lazy Susan disc. The difficulty we faced was that the center of the crown box had to match with that of the disc to ensure that the whole mount rotation will be smooth. Thanks to Lum's careful measurements, this challenge was overcome. We needed to install the rest of the mount onto the mica crown box. Lum took responsibility for this phase. It was challenging as a mount error can lead to a failure of the system, like the motor can't rotate the PVC pipe or the mount. Firstly, Lum drilled holes for the bearing and servo motor. Special thanks to Anfu for helping us with this step. The two holes needed to be exactly on the same line to function as a rotating axis for the PVC pipe. A petite measurement mistake can result in the PVC pipe failing to rotate. Finally, we attached everything onto the mica crown box with the help of the bolts and L-shaped connector. It's time for a small test for the servo motor. Fortunately, it could rotate the pipe. However, it's burned unstably. The servo motor also used a current of almost 2 amperes and started to hit significantly. I had to stop the test and immediately consulted with Yoon, Tae-won, and Yu Feng. It turned out that the rocker boxes were attached loosely to the crown boxes, making them vibrate unstably when the servo motor operated. The next day came, and Yu Feng made us a U-shaped mica that could keep the rocker boxes tightly attached to the crown board. We installed the part in the rocker boxes and used more bolts to tighten them. The solution worked well. And here comes the third step, CNC cutting. We plan to build a solid, stable stand for the whole mount so that the reverse problem would not re-happen. Thanks to Chú Thái, I could use the CNC machine to cut 10 round wooden plates with a diameter of 300 millimeters. However, things did not go well at first. Because of an error in the setting of the CNC file, we could not manage to get the drill bit drilled through the MDF board. We have to diagnose the machine for an hour before we found the error was actually because of the CNC file. After that, Chú Thái managed to get the drill bit through the MDF board and cut 10 wooden plates for our team. Then we glued the plates together. Chú Phương helped us to drill 2 holes for placing the wires. Eventually, we tried to put the whole mount onto the wooden stand. However, the inside wooden part was too high for us to put the azimuth servo motor onto. Long and I tried desperately to green it to make it lower, but it was hopeless. But we can still come up with a solution. To chisel and make a hole to put the servo motor. Special thanks to Nhật Tân for helping her with this. Thanks to the hole, we could put the servo motor into the wooden stand. In the clip, Long tried to glue the servo motor to the wooden stand and tried to get it dry fast. We also faced another difficulty in connecting the wires. I wanted to build a parallel circuit, so the best solution to connect the cables was to solder them together, and I would like to thank Human Trang for helping us with this part. And yay, we're done. Now it's time to plan a test to check if everything goes well.
Testing toolbox is an important step that most of us often forget or carelessly prepare. However, it critically decides how successful the project is. To our product, because of the demo version, we will not test it with the real sky or real stars. So how can we decide the accuracy of our product? Well, leveraging the attitude and azimuth degree in selenium path. For example, you can see here we have selected Sun with the azimuth is 257 degree, attitude is 51 degree. We will know how much degree the telescope should rotate. We also have equipped the telescope with the degree decorated on the surface look like this. This user can relatively check the attitude and azimuth degree while playing around with our product. The confidence level of this testing method is approximately 80%. In the future, we expect to increase this kind of number by equipping the telescope with the compass sticking inside the telescope. Other testing plans can be proposed and rolled out soon.
As you may know, our product failed to run on the demo day. However, for some very magical reasons, our product could run again right after the demo presentation. Hence, we took it as a chance to let the user test our product.
Đây là product sau buổi showcase.
Dạ đúng rồi. Rồi bây giờ thầy nhấn vô current object để cho nó biết. Dạ.
Rồi.
Dạ, thầy nhấn slew thì cái kính nó sẽ quay.
Slew là để cho cái kính nó quay theo nó.
is aware of its strengths and weaknesses, so we divide tasks equally and assess one another as needed. True, it wasn't an easy journey to make these products. There are many factors to consider, such as you should be cautious about the errors in measurements, always plus or minus a delta, or having a clear sketch with no vision will make the process easier. Miscommunications sometimes occur, and it is best to learn that we must be on the same page. Expect the unexpected as well. There were things at the beginning that looked negative, but it turned out that there are solutions or perhaps innovative ideas to get things on the right track. At the end of the day, everything was fine. We kept smiling and encouraged each other. 5 people from different backgrounds have such fun moments and support each other so much. So thank you. Thank you, my team, for their hard work and always be supportive. Thank you for this journey.